In the last lecture, we analysed how we can use an instrumentation amplifier to detect the difference signal appearing at the input while rejecting the common mode signal. In this lecture, we're going to look at how we actually design an instrumentation amplifier and improve its performance so you can use it in circuits and applications that you find in your projects and in your future careers. The key to instrumentation amplifier is based around a traditional difference amplifier. So let's take a first shot at building an instrumentation amplifier. And here we have our two different differential inputs, and we have a reference input and a sense input, similar to what we had before, and the output in the present is not connected anywhere. So let's look at how we define it. First of all, we join our output to the sense connectors, and we join the reference to ground. The triangle we should assume is a perfect triangle, and we can now do the analysis around this circuit to find out what the transfer function is and the performance will be. It's a perfect op-amp, so we can assume that Vn equals Vp, and we can also calculate out Vn and Vp. This here is Vn, and this here is Vp. So we now have both sides of the equation, and we can calculate out basically that defines that the sense, which equals the output signal, is the difference between the two input signals plus the reference. And in this case, because the reference is 0, effectively we're saying that the sense, or the output, is the absolute difference between what appears at the input and what appears at the output. But right now we only have a gain of times 1. Can we improve on that? So let's see if we can design a similar difference amplifier but with a gain of greater than 1, because that would be more useful to us. In this scenario here, we have the same design, but we've defined the resistors as R1 and R2. And doing the similar analysis as we did before, we can calculate out the signals at both inputs, make them equal because it's a perfect op-amp, and that lands up with basically saying that we can now define a difference amplifier with a gain greater than 1, and the gain is equal to R2 value divided by R1 value, which is very similar to the equation for an inverting op-amp. This circuit rejects common mode signals because the whole circuit is symmetrical. But problems arise when resistor tolerance makes the circuit non-symmetric. And the worst case error would be when the resistor sides on the positive and the negative inputs are actually maximally unbalanced. And for this analysis here, we'll assume that all the resistors are 1% tolerance, but it could be anything. Looking at the analysis here, R2 over R1 would be approximately 2% small, because R2, the gain is defined by R2 over R1, and R2 is smaller than R1 by 1%. On the other leg, the gain is 2% high for exactly the same reason. So we need to try and calculate out what the effect of this mismatch of resistors would actually be. From examination, it's easier to actually do the analysis if we collect all the errors onto one resistor. So what we've done here is we've actually said, let's assume that this resistor here, R2, is 2% high, and this resistor here, R2, is 2% low. So we can now do the calculations in exactly the same as we did before, and before we get much further in the analysis, It's important to realize that the delta figure in this example here is actually in ohms, not in percentage. So the total error, delta here, could be actually up to 2% because you would get 1% error from R1 plus 1% from error from R2. Just to make the maths more easy, we've assumed that the differential gain of the difference circuit is approximately 1. Therefore, R2 is going to be equal to R1. So replacing that into the circuit, we can see that we've got R1 plus delta and R1 minus delta here. Now what we want to do is calculate two different sets of analyses. We want to calculate out the common mode gain, and we also want to calculate out the differential gain. But we want to do these two things separately so we can actually compare the impact of these on the final result of the circuit. In the case of the differential one, let's let In plus equal the negative of In minus. And we'll call this difference voltage divided by 2. In other words, the full input voltage is VDiff, but in the case of I plus, it is going positive, and in the case of I minus, it's going negative. Doing the analysis in the same fashion as we did before, we land up with the two equations here. And because we know that the delta, which is the tolerance or the error in the resistors, is much, much smaller than R1, and for 1% resistors, delta would be approximately 2%, then we can actually make an approximation that says that this equation here is approximately 1 over 2. So our difference signal is equal to the sense minus ref. In other words, it's the differential gain is times 1. Now let's look at the common mode gain, and going through precisely the same analysis, but in this case we're saying that in plus is equal to in minus because it's a common mode gain we're looking at, and we're going to call that VCM, the common mode voltage appearing at the two inputs. So running through the analysis, we land up that, again, if delta is much less than R1, then we land up with a common mode, the output voltage times 2 times R1 is approximately the common mode voltage times 2 times delta. So we land up with a common mode gain, which is delta divided by R1, which is effectively the same as the tolerance of or 2 times the tolerance of the resistors. In this instance, they're both ohms, but when you plug them in, you'll land out that if R1 is in ohms, then delta must also be in ohms. What we've proven is that the resistor mismatch for 1% gives a relatively small error in the differential gain, but actually has quite a considerable impact on the common mode gain. So now we can look at the common mode ratio for the difference amplifier as a differential gain, which is 1, divided by the common mode gain. So we land up with a common mode rejection ratio of 1 over 2 times the resistor tolerance. And putting some numbers against this, if we had 1% resistors, our common mode rejection ratio would equal 50, which, when expressed in decibels, is 34 dB. If you increase the quality of resistors to 0.1% resistors, the common mode rejection ratio would rise to 500, which would be 54 dB, i.e. 10 times more than the previous version. Let's go back to our difference amplifier and look at the impact of how it might behave when we actually do the analysis again. What we have here is we have our two input terminals. We've got our mismatches here due to the tolerances, and delta is 2 times the tolerance of resistors. And what you discover is that any error here, which could be used to contact resistance or circuit board tracks or even thermocouple wire resistances, will actually give rise to an error, because these two series resistances actually add to the R1s here, and they will actually change the gain. And if those two resistors are not absolutely matched, they will actually give an increase to the common mode gain of the amplifier, which is exactly what you don't want. How could we improve that? An obvious solution would be to use two buffer amplifiers. These are two op amps connected as ×1 buffers, and they would take away any variation in the resistance, because the input resistance looking in here and looking in here is very high. So any errors due to resistors or cable length would be swamped by a very high input resistance into the amplifier. So that would solve that one. However, it doesn't solve the resistor matching problem. And the best case matching you can get for resistors you can buy from suppliers, you can get about 0.01% matching. Whereas if you buy a monolithic solution, i.e. one that's been manufactured on a single substrate, either be it silicon or ceramic, such as the Texas Instruments 105 or Analog Devices AMP03, you can actually get approximately 10 times better performance, because they can control the temperature and the tolerance of all the resistors on their substrate. That sounds pretty good, but let's look at how it performs when you actually apply it to a circuit. We have here a bridge amplifier. This is a Wheatstone bridge. It consists of 4 identical resistors, and it operates by placing a voltage across the resistors. These 2 resistors here are perfectly matched, so you get 0.5 volts out, whereas this resistors here allow this resistor to change with the load that's being applied to the bridge, and the output signal would be about 1 millivolt. We'll talk more about this in a second, but in the scenario here, if we wanted to see anything at all, we would need a common mode rejection ratio of about 54 dB before any error due to common mode gain would be less than the error, the signal we want from the different signal coming out of the bridge, because the output signal is about 1 millivolt. That signal is what you would expect to see at full load. But if we wanted to measure, say, with a resolution of 1 gram in 1 kilogram or 1,000 grams, we would need a common mode rejection ratio of 114 dB. In other words, 1,000 times more than the 54 we calculated. And that's beginning to get really, really tough. It would require hugely expensive resistors, then they would have to be trimmed, and then they would need to calibrate the circuit. And we'd need to do that regularly. And that is not a workable solution for mass-produced electronic products. Just so you're clear that this is a realistic scenario, and you're going to see this when I give you out your assignment, this is actually a load cell. And the rated value of the ones I've given here can be either 3, 5, 10, 20, 30 or 50 tons. But look at the output. The output for full load is only 1.5 millivolts per volt applied across it. Now you can certainly apply up to 10 volts across the bridge, but nevertheless, even with 10 volts, it's only 15 millivolts. So it's a really difficult challenge to detect the amount of weight being applied to this load cell in the presence of common mode signals. How do we do this? How can we design a circuit that will actually allow you to sense approximately 1 gram in 1,000 grams or 1 kilogram in 1 ton? We'll look at that in our next lecture, and what will be our final lecture on instrumentation amplifiers. Thank you.